Thank you very much. I'm Gabe Kaptchuk. I'm excited to talk to you about this work. This was joint work with Matt Green and Hias from Johns Hopkins University, myself from Boston University, Matthias from Aarhus University, and then two folks from industry, Eric and Benjamin from Trail of Bits. And this is going to be a little different than the other things that have been going on in this talk. We made a choice to omit the word zero knowledge from the title of our paper, and therefore it looks like an attack paper when in fact it's a little bit more of a crypto paper. So I apologize for having to shift your brain a little bit. So in case you haven't looked at zero knowledge for a while, let's just quickly remember what the notion means. So we have a prover and a verifier. And the idea here is that the two of them agree on some NP language and a particular instance of the language. And the goal of a zero knowledge statement, or sorry, a zero knowledge proof, is that they're going to engage in some kind of protocol such that the verifier is convinced that this instance is indeed a member of the language. And the whole point is that they're not going to learn anything besides membership in the language. In particular, right, if we represent this language using its relation function, right, we have some instance X and a witness W, and we don't want to leak anything about the witness at all, right? So you just learn this output bit 1. Right? And zero knowledge has kind of become an important part of the cryptographic literature, and as such there's been a lot of new techniques developed since its initial invention in the 80s. In particular, a lot of the way that these zero knowledge proofs work is that either you look at the particularities of the language and you develop a custom protocol that only works for that one language, or what you do is you represent this relation function as a circuit, and then you appeal to some kind of natural NP reduction, right? So in particular, when you represent this as a circuit, you just use circuit satisfiability, and there you have an NP function, an NP relation, and all of a sudden you have kind of generic zero knowledge that works for everything. Right? And zero knowledge is a really interesting primitive from a cryptographic perspective, but the story goes that when the idea of zero knowledge was first being introduced by Goldwasser, Mihaly, and Rakoff in the 80s, they had to shop their paper around a number of times, and it kept on getting rejected until eventually it got accepted. And part of the reason they had to shop their paper around is that everybody looked at the notion and said, well, I don't know what I would possibly use this for. Hey, is this even interesting? I can't figure out what zero knowledge could be potentially used for. And that was kind of the way that zero knowledge has been introduced into the world. This question about what exactly are we supposed to use this seemingly cool notion for. And so in the intervening years, we have found a couple of interesting use cases for zero knowledge. In particular, Schnorr introduced this identification protocol that you could use to kind of prove your identity to somebody without allowing them to imitate who you are. Similarly, this could then be flattened down and be used into a signature scheme, which is pretty cool, except we have other signature schemes, and not that many people have actually ended up using identification protocols in and of themselves in practice. More recently, zero knowledge proofs have been an interesting tool in constructing post-quantum cryptographic primitives, in particular signatures. The picnic protocol was a finalist for NIST's recent PQC signature competition. And so that seemed like a cool use for zero knowledge, but of course it wasn't actually selected as one of the things that was standardized. We had other techniques that were used, so zero knowledge, once again, is not really something that we're using directly. And then there's a whole host of blockchain-related things that you could potentially do with zero knowledge that might have to do with the privacy of your transactions, or maybe you want to do some kind of compression thing. There's a lot of things in that space. I'm going to leave those aside for the moment. So when we started kind of thinking about the beginnings of this project, we really wanted to find a way to use zero knowledge kind of directly in a way that was interesting for an application and something that was new and fresh. And so one of the first things we did is we looked at software exploitability as a potential place where zero knowledge offered a new solution that wasn't available using other tools. So many of you might be attack people. I'm a cryptographer, so I apologize if I get something in the attack space wrong, right? But in the software exploitability world, the big thing that's going on is bug bounty programs. Right? So companies might say, we will pay you a certain amount of money if you can come to us with a vulnerability in our system, and then we'll patch the system, we'll give you some money and give you some credit, and that will work really well. And so there's large numbers of people who are working on vulnerability research, trying to find bugs in systems in the hopes of actually getting some money from these programs. So how do these things actually work in practice? We have a vulnerability researcher who's going to spend a whole bunch of time maybe looking at a compiled binary, maybe looking at a website, whatever it is, and trying to poke it in a bunch of different ways, maybe reverse engineer it, try and figure out what's going on, until eventually they find some input to the program that should force the entire system into an incorrect state. Right? They should get around maybe some password protections, or maybe use a buffer overflow, something like this. And then there's a bug bounty administrator who's in charge of actually issuing a reward once the vulnerability researcher kind of discloses, yes, I have found a thing. And oftentimes these vulnerability researchers, they might be part of large companies, but more likely they're actually an independent researcher. There are one or two people who are working together to try and figure out how to make this work. So in order to disclose an exploit, what would happen is that the vulnerability researcher would send their exploit to the bug bounty administrator. The administrator would look at it, evaluate it, and then figure out how much money they wanted to give back to the vulnerability researcher. Right? And this is a problem because as soon as you engage in this interaction, the exploit is immediately released. Right? That is to say, the bug bounty administrator knows what the vulnerability is, and so there's kind of no more negotiation potential possible for the vulnerability researcher. If you look at the power dynamics here, right, you might have an individual vulnerability researcher, but a large company running a bug bounty administrator, or administering a bug bounty program. Right? And so this is a problem, right? What if the exploit in the vulnerability researcher's mind is worth a lot of money? It's a huge, huge vulnerability in the system, but the bug bounty administrator doesn't think so. They want to give them like $2,000 for the last 3 months of their work. Right? This is not a good situation. Right? So instead of just sending the exploit over, you might want to do something else. Right? So one potential thing you could do is you could take a video of your computer running the exploit, and you say, haha, right? I showed you, I ran the program, I ran it on my secret input, and it forced it into this bad state. Right? The problem of course, like a video can be doctored, and it's not reliable. Right? So this doesn't really necessarily convince the bug bounty administrator that things are really happening that way. So I've kind of set up this visual in a very obvious way about what we want to do next. Well, why should we use these things that are not mathematically precise, that don't have good soundness, when we could just rip out this video nonsense and replace it with a zero-knowledge proof? Right? We're going to somehow have the vulnerability researcher produce a zero-knowledge proof that they actually have an exploit, give that proof to the bug bounty administrator, negotiate for a reward before releasing the exploit for patching. Right, there's a couple of other important kind of ways you could use this system. One is if the bug bounty administrator is not being responsive, you could actually post this proof on the internet and say, hey, right, I have a vuln for your system. You need to respond to my email right now. I'm entering disclosure, right, and we need to get this going. Right? And this would kind of force them in a kind of public way to respond. Alternatively, right, if you have a system that's no longer being upkept, that there isn't actually an active bug bounty program for, and you want to tell everybody in the world, hey, we need to stop using this software because it's bugged, right? I have a vuln. You don't want to post the vulnerability on the internet to prove this to people, right? That's not a good idea because all of a sudden the system is vulnerable. So instead you can post a zero-knowledge proof saying, hey, I really have a vulnerability in the system. We need to start transitioning away immediately. So we kind of set out to study the problem of software exploitability. And there's been a couple of other approaches in the past. So one approach from Heath and Kolesnikov in 2020, what they did is they took source code, and what they did is they compiled it into a circuit using a custom compiler, and then they would run zero-knowledge proofs over those circuits. So the problem with this approach is that you really need access to source code. And oftentimes, if you're a vulnerability researcher, you don't have source code. If you had source code, it would make your life a lot easier. Instead, what you have is a compiled binary that you have to interact with, right? And there's no way to get this to work out. By compiling source code into a circuit, you really get a tight binding between the source code itself and the circuit, right? You can't kind of think about how the system would actually run on real pieces of hardware, which is oftentimes where you're able to actually find an exploit. Another approach from the literature is you actually emulate RAM computation. So you kind of build a very specific circuit that kind of pretends to be a RAM computer, and then what you do is you again produce a proof of correct execution on a RAM machine. This has been known, we know how to do this for about 10 years now, and in general the way that you do it is you define a custom language, a custom ISA, with custom instructions, and the reason to do this is that you want a very, very small set of instructions to reason over. So the kind of leading example of this is an ISA called TinyRAM, which is not ever implemented in hardware, but is implemented kind of as a logical way to think about RAM machine operating. So what we do is kind of build off of each of these approaches, and we say, no, we're going to get the best of both worlds here. So we're not going to need source code, and we're not going to define our own custom ISA. We're going to work with a real, actual processor language and produce proofs that show when I run this particular binary on this particular system, I have an exploit. So how do we get this to work out? So this is our approach that's inspired by prior work. The idea here is that we take some initial state of the system, and we iteratively kind of take the processor ISA and apply it to the state, and eventually kind of keep updating it over and over and over again, where each of these processor updates kind of represents a state transition, and importantly, the state transition is over real processor semantics. So we do this over and over and over again, and eventually we get to a place where the final output of the state can be revealed and say, hey, look, this is not a state you would expect the system to be in. Right? And so what we're able to do is take this entire thing, compile it into a giant circuit. I'm cheating here a little bit. There's a bunch of things about memory that I'm not really dealing with here because I don't have time. So we have to deal with reads and writes to memories, and it's a whole bunch of overhead. And so what we did is we tried to evaluate the system on an actual ISA. We looked at the microcorruption embedded CTF challenges. This is for a microcontroller, not like a full CPU. And tried to actually say, OK, if we want to instantiate this in practice, can we make it happen? There's a lot of challenges to making this work, both theoretical and a tremendous, tremendous amount of engineering effort that makes this work out. I don't have time to go into all these things, but just to kind of highlight one of the challenges here, we need to kind of emulate syscalls. And syscalls are not usually they're not actually in the ISA directly. So you somehow need to kind of cross the software-hardware boundary in weird ways in order to capture all the semantics of running a piece of binary on an actual machine. When you want to choose a zero-knowledge system, you make, there's a lot of choices you can make here. So when we were looking at instantiating this, the first question you ask yourself is whether or not you need interactivity. Turns out we did not. Turns out we don't support interactivity. And I'm going to skip through the slide for time. We ended up choosing an MPC in the head zero-knowledge system, which is incredibly efficient for provers. So we were able to take the KKW 2018 zero-knowledge system, which is MPC in the head base. We produced a very efficient Rust implementation with a bunch of low-level optimizations I don't have time to talk about here. We compared it to all the prior work, and basically the prover time is like blazing fast compared to any of the things that you might want to use for succinctness that are oftentimes used in blockchain production systems. Basically, we take all these ideas, we assemble it into an end-to-end system. Again, it's hard to emphasize the amount of engineering effort that went into this. There's a whole giant circuit compiler that automatically assembles this giant circuit. And we were able to then plug this into the microcorruption CTF challenges and actually prove that, yes, we do have a working exploit for all of these challenges. Some of them run super fast, right? If there's a password in the binary, it's pretty easy to be like, yes, if I put this password in, it exploits the system. And so the resulting proof is actually quite small, 295 megabytes. The verifier runs in only 7 seconds. Things are great. If you want to do something much more complicated, like a format string vulnerability, the proofs start to get pretty big. They're in the gigabytes. Verifier time's 63 seconds. Prover time, 89 seconds. Yeah, that's a little bit slow, but the truth is, compared to the thousands of dollars they're getting passed around in actually paying people for their work, this is still relatively small in compute time. You could run this on a laptop or a relatively large, you throw it on Amazon Cloud, pop back the proof, and stick it on the internet without revealing information. I'll say there is some follow-up work coming in the next year or so if you're interested in this, keep an eye out. And with that, I'll say thank you very much.
Okay, just check if there are questions. If not, I have a few burning ones because I'm not a cryptographer. I'm an attack person. And so my question is really, I have a few, but let's go with this one, is about the speed. So like you talk a lot near the end of the talk, especially on how kind of efficient these things are, but I don't really see practically why it matters that it's very fast in this case.
Yeah, so I think the reason to worry about efficiency is that when you don't do cryptography carefully, efficiency really, really goes to hell, right? So we wanted to make sure that it wasn't taking you like, a year and a half to compute your proof. Obviously, the difference between like 85 seconds and like a day of computation time is probably not that much. But if you want to outsource this and put it, on a cloud computation on a big server, you don't want to pay, hundreds of dollars in compute time. You want to pay tens of dollars in compute time. So we're trying to make it realistic, especially as we scale up into things like x86, where things get much more complicated.
good. And because we're a little ahead, I'm going to ask my second question, because we don't have any else here, which is like, at the end of the day, there are real users at the other side of these systems that have bugs in them, probably. And so my question is more like, now that you've created this system which allows this kind of negotiation to happen, doesn't it increase the risk that bugs don't get fixed?
Yeah, so again, I'm not an expert in this space, and I'm not a participant in this space, right? So, thankfully we had to rely on some of my co-authors who had more familiarity. Our understanding is that we want to incentivize people to actually do the vulnerability research, that is ultimately the bottleneck here. And so what our system ends up doing is actually kind of allowing those people to make sure they're getting paid and supported, and they can make a living out of doing this work. If they can't make a living out of this work, I would argue that fewer bugs are going to get fixed. It's obviously, it goes both ways, and I think, as is oftentimes true with crypto, it could be used in a way that is not great, but I think we're pretty hopeful about the idea that this could be used in order to incentivize more work in the space.
Excellent answer. Thank you very much.
Yeah.